We're going to do a lot of derivatives this quarter, use them for all sorts of different types of things, and we're not going to want to go back to do the limit as h goes to 0 every single time. So we're going to try to come up with a bunch of sort of shortcut rules for taking derivatives. Let's start pretty simply. Suppose you've got f of x equals a constant. I'm hoping you got an idea what the graph of that thing looks like. I'll draw the graph in red here. It's a horizontal line. And so the question is, when you're taking the derivative, so when I, oops, equals a constant, yeah, that's a c. So what's f prime of x? Well, for any x value, I'm saying what's the slope of the curve at that point? What's the slope of the curve right here? What's the slope of the curve right there? What's the slope of the... It seems it doesn't matter what x value you plug in, the slope of that function is equal to 0. It's a horizontal line. The slope is always 0. Right? We could prove that. Actually, let me do a quick proof of that. If I look at the definition here as the limit as h goes to 0 of f of x plus h minus f of x all over h, well, the thing is f of x plus h is c. F of x is c. Right? So this is 0 over h. Okay. Now, yes, h is going to 0, but the numerator is always 0. So, you look at x plus h here, the slope of the secant line between those 2 points is 0. For every value of h, the slope of the secant line is 0. The slope of the secant line is 0. Just h gets smaller and smaller and smaller. The slope of the secant line is always 0, and so the limit of all those zeros is 0. Okay. I think the picture is pretty intuitive, though. Just you see the slope is 0 everywhere, so the derivative should be 0. Everywhere the slope is 0. Another one that I think is fairly intuitive is if you look at, well, let's do this one. What if we just have f of x equals x? You got an idea of what that looks like? That's just the graph of y equals x. Right? When I say what's the derivative, I'm saying for any x value at this point, what's the slope of the curve right there? Well, that curve is a straight line and it has the same slope everywhere. Everywhere. No matter what x you plug in, the slope is equal to 1. So for the function f of x equals x, the derivative function is f prime of x equals 1. The slope is always 1. Okay. And maybe you can even see the next example. If I have f of x equals, mx plus b, right? Just your standard line with intercept b, slope m. That's the x-axis, that's the y-axis. When I talk about the derivative, I'm saying for any value of x, you tell me what the slope is at that point. And the thing is, the slope doesn't change. No matter what x you give me, the slope is always equal to m. Then I'm willing to say that the derivative function is this constant m. No matter what x you tell me, this function has a slope equal to m at that x value. Okay. So those are pretty straightforward. When you got a straight line, the slope is always the same, so the derivative is a constant function. Okay. Now let's look at some other ones. In the previous section, we looked at some quadratic and maybe a cubic one even. I wanted to do x to the n in general, so I want to look at f of x equals x to the n. Now with n equals 1, I think that's what this one is right here, right? This is x to the 1 power. But now I want to be able to do x squared or x cubed. Actually, x to the n for any, n is any positive integer. Positive integer. So 1, 2, 3, 4, 5, 6, and so on. Integer. There we go. So how am I going to do this? Well, I don't have a shortcut rule yet, so I'm going to go back to the definition of derivative. So this is the limit as h goes to 0 of f of x plus h minus f of x all over h. This is just the definition. I haven't done anything yet. I'm going to apply my function to this now, or apply this to my function, whichever way you think of it. This is the limit as h goes to 0. Now f of x plus h is x plus h to the n, and then minus f of x, that's just x to the n, all over h. And I realize here that my n's and h's look kind of alike, so I'll be a little careful. That's an n. Okay, it's an h in the denominator, that's an h right there. Now, I'm going to multiply this out. If you look back what we did when we had an x squared, we multiplied it out. When we had an x cubed, we multiplied it out. I want to multiply this out. Now, how do I multiply it out? Well, I'm going to do a little bit of work down below, and then I'm going to come back up here to this. So I'm going to scroll down a little bit. I want to notice what is x, stop. What is x plus h to the 0 power? Right? Well, anything to the 0 power is 1. What's x plus h to the 1 power? Well, that's, of course, just x plus h. One thing I want to notice here are the coefficients. This coefficient was just a 1. This was a 1 and a 1. Okay. X plus h squared. Well, you got to FOIL it out, right? That's x squared plus 2x h plus h squared. So this is a 1, 2, 1 for my coefficients. X plus h cubed, so if I take this thing right here and then multiply it by another x plus h, so that's kind of a big FOIL now, that would be x cubed plus 3x squared h plus 3xh squared plus h cubed, and the coefficients are 1, 3, 3, 1. I'm going to do one more here. X plus h to the 4th power. So take all of this right here and multiply it by another factor of x plus h. You're going to end up with x to the 4th plus 4x cubed h plus 6x squared h squared plus 4x h cubed plus h to the 4th. There we go. And the coefficients are 1, 4, 6, 4, 1. Now, some of you have seen this pattern before. You may recognize this. This is called Pascal's triangle. Each row of Pascal's triangle is gotten by, you start with a 1, and then you add up the first 2 terms there, and then you add up the next 2 terms, and you add up the next 2 terms, and you add up the next 2 terms, and you end with a 1. And it turns out that Pascal's triangle shows up in a couple different kinds of places, but here is one of them, the coefficients of a plus b to the n, or in our case x plus h to the n. Right. The thing that I notice that I'm going to use for what we're doing is this column, just sort of diagonal, I guess, right here, right? That number, oops, I did want that circled, that number is the same as the exponent. That's a 1, that's a 2, that's a 2, that's a 3, that's a 3, that's a 4, that's a 4. When you're doing an x plus h to the 5th power, that's a 5. Right? And that coefficient is sitting right here. It's the second one in here. And the variables are always x to the 1 less power and h to the 1st power. Okay. So the thing that I want to do is I want to come back up here and say, okay, so when I multiply that out, this is going to look like the limit as h goes to 0. There's going to be an x to the n, and then there's going to be a plus n times x to the n minus 1 times h, plus a bunch of stuff. And all that stuff is all of the stuff that's, these things over here. And that's so if you notice, the powers of x go down by 1 each time, and the powers of h go up by 1 each time. So everything over here has an h squared in it or more. All right, and that's what I want to do. I want to call this stuff with h squared, and then I've got that minus x to the n. Right? There's a bunch of stuff there, depending on how big n is. Right? And then it's all over h. The point is, it's all going to go away when h goes to 0. But what I have here now is I have, where's my red pen? This and this cancel out. And now everything that's left in the top has at least one factor of h in it, and this stuff has at least 2 factors of h in it. So let's factor out an h from the top. So now I'm looking at the limit as h goes to 0. I'm factoring out an h, so the first term here is nx to the n minus 1, and then all this stuff had at least an h squared in it, but when I factor an h out, so it's got at least a factor of h in it. So this is just stuff with h, and then I'm dividing by h. Right? The thing is, if you take a look at the proof in the book, they actually give some of the coefficients for these things. But it's not going to make any difference what those coefficients are, because when h goes to 0, all this stuff is going to go away. Okay? At the moment, we have it with our factor of h on the top and the bottom, and we can cancel those out. That's the factor of 0 divided by 0, 0 on the top, 0 on the bottom. Now I can plug everything in. I've got nx to the n minus 1, and then stuff with a factor of 0 in it, because the h is now being substituted by 0, and all that stuff is just 0. So what's my conclusion here? Let me get this stuff out of the way. What's my conclusion? Shoot, that's not going to work. Let's try that again. Yeah, there we go. Move that out of the way. My conclusion is that for f of x equals x to the n, then f prime of x is nx to the n minus 1. Right? Sometimes that's written this way. The derivative of x to the n is nx to the n minus 1. I want you to get used to both notations here. Let's do a couple of quick examples here. If I have the derivative of x squared, that should be 2x to the 1, right? The exponent comes down in front, and then you drop 1 to the exponent. The derivative of x to the 5th power is 5x to the 4, right? The derivative of x to the 17 power is 17x to the 16. I'll tell you, I really would not want to do the limit as h goes to 0 of x plus h to the 17 minus x to the 17 all over h and have to multiply that thing out. Yeah, that wouldn't be, well, it might be fun, but it would be a lot of work. This is just much quicker. The exponent comes out in front. Okay. One last thing I want to say about this is that although the proof is really only good for integer values, positive integer values of n, this actually works for anything. This is for any n. If you have f of x equals x to the n, then f prime of x will be nx to the n minus 1. As we do more and more types of functions, we'll be able to prove it for different types of n, but just let's make it known here to begin with that this actually works, and that, so for instance, if you took the derivative of x to the pi power, it would be pi x to the pi minus 1 power, not n minus 1, pi minus 1. Okay. It works for anything.